All right, welcome to section 9.2. We're going to start talking about series. So, series is basically taking a sequence of terms and adding them all together. So, an infinite series, or just series, is where you will find the summation of n equals 1 all the way into infinity of some sequence function. So, it's basically, like I said, we're just going to add up all the terms of a sequence all the way out to infinity. So, these are called the terms of a series. So my series could be finite series, or what we call partial sums. So let's say we only wanted to go to n instead of infinity. Well, then we have what is known as the sum of the first n terms of a series, and those are called partial sums. So we will identify this with a capital S with a subscript number telling us how many terms of a particular sequence that we added together. So S sub 1 is just the first term, A sub 1. S sub 2 is equal to A sub 1 plus A sub 2. S sub 3 will be the sum of the first three terms, and so on and so forth until you get to S sub n, which is the sum of the first n terms of a sequence. So this is what we call our nth partial sum, or if you want a specific value, you'd say your third partial sum, fourth partial sum. In this case, the nth partial sum. So now partial sums themselves, they also form a sequence. So we'll have S sub 1, comma, S sub 2, S sub 3, all the way out to S sub, if you want, infinity. So if S sub n, the series of your partial sum sequence, converges to S sub n, which we basically say S. It's like saying there's a limit. Then the series, the summation of n going from 1 to infinity, A sub n, converges to S, and S is called the sum of the series. So again, not sure why I put that subscript in there, because it's just little s. So by our definition, again, given our series, S sub n, those are your partial sums. If you go all the way out to infinity, then it's an S. If it does go to infinity, I like to write S sub infinity, so it kind of matches this S sub n. And like we said, if the limit goes to some S, then that sum of that series of partial sums is going to be the sum of the original series, A sub n. So if it converges, then we have a sum for the original sequence. That's the limit of the partial sum series. And of course, if there is no limit, then it's divergent. We can't find the sum of this because it's probably heading out towards infinity. So if we look at an example, apply the previous definition. Let's say our sequence function is A sub n is equal to 2n minus 1. We'll write out a few terms of our sequence. So this would be, okay, n is 1, 2 minus 1 is 1, n is 2, 2 times 2 is 4, minus 1 is 3. Okay, because it's linear, then you're always going to be increasing by 2, so this is the sequence of odd numbers. So it's 1, 3, 5, 7, 9, 11, out to 2n minus 1 plus all the way out to infinity. So let's find a few partial sums. S sub 1 is 1. S sub 2 is 1 plus 3, which is 4. S sub 3 is 1 plus 3 plus 5 equals 9. S sub 4 is 1 plus 3 plus 5 plus 7 is 16. Add the 9 to its 25, and we can keep going forever. Now, we're going to start looking at then the limit of this, but again, you'll probably understand that based on what this function, our sequence function, is doing, it's always getting bigger. And if we keep adding these together, we can see we're going out to infinity. So just bear with me through the steps. Step 3, examine the sequence of partial sums and find a formula for the nth term. So if I'm 1, 4, 9, 16, 25, these are perfect square numbers. 1 squared, 2 squared, 3 squared, 4 squared, 5 squared. So if I go back to here, 1 squared is 1, 2 squared 4, 3 squared 9, 4 squared 16, 5 squared 25. So my partial sum sequence function is n squared. Well, now if we find the limit as n approaches infinity of n squared, we know that's going to infinity. This doesn't exist. It diverges, and therefore this summation is also going to diverge, which means we can't find its sum. It goes too big. Okay? And I agree, you probably could have seen this if we tried to find the limit of 2n minus 1. As n goes to infinity, we can see that the numbers constantly get bigger, so of course as we add these terms together, so must its sum. But we're interested is when does it converge? When can we take the limit of this sequence function of our partial sums? And when does it equal a limit value that we call little s, and then that's going to be the sum of our original sequence function a sub n. All right, so looking at example 2, determine if the infinite series of a sub n is equal to 1 over 2 to the n converges or diverges. Writing out some terms, 1 over 2 to the n, 1 half, 1 over 2 squared, 1 fourth, 1 over 2 cubed, 1 eighth, 1 over 2 to the fourth, 1 16th. Step 2, start to write out your partial sums. 1 half plus 1 fourth, or we could say 2 fourths, plus 1 fourth, 3 fourths. The sum of the first three terms, 4 eighths, 2 eighths, 1 eighth, add up to be 7 eighths. S sub 4, denominator 16, that's going to be my common denominator, 8 over 16, 4 over 16, 2 over 16 adds up to be 15 over 16. And I can start to see a pattern in my fractions. The top number is always one smaller than the bottom. So we'll call that 2 to the n minus 1 over 2 to the n. 2 to the first, 2 squared, 2 cubed, 2 to the fourth, and then 2 to that n power minus 1. So again, if we take the limit of the partial sum sequence, all right, so here, write this as two fractions. 2 to the n over 2 to the n minus 1 over 2 to the n. As n goes to infinity, all right, we can do some simplifying. This will become a 1, and this limit is going to become 0. So 1 minus 0 is 1. So not only does our summation up here converge, but we've just found the sum of that series. So as this goes out to infinity, it adds up to be 1. And we'll look at some more when we come back in part 2.